Okay, good morning. So, today we are going to start the second unit, that is gate level modeling. Okay, so for today's presentation also, I have referred the same textbook, that is designed through Verilog HDL by T.R. Padmanabhan and B. Bala Tripura Sundari. Okay, now let us start the session. So, in the unit 2, gate level modeling, we have these contents: introduction, end gate primitive, module structure, other gate primitives, illustrative examples, tri-state gates, array of instances of primitives, design of flip-flops with gate primitives, delays, strengths and contention resolution, net types, design of basic circuits. Okay, now let us start with the end gate primitive. So what is this end gate primitive? Okay, so one thing we have discussed in the last class is that in Verilog already all the basic gates are available as readily module. All the basic gates are available as ready modules. So those are called gate primitives. Gate primitives, that means all the basic gates are available as ready modules in the Verilog. We call them as gate primitives. Okay, so wherever that particular gate is necessary, we just instantiate that gate in our program. Okay, now let us assume this AND gate primitive is there. Okay, already the AND gate primitive is there inside the Verilog language program, in the Verilog. Okay, now how we can instantiate this AND gate primitive? Okay, let us see with this following statement, that is AND space G1 within brackets O comma I1 to IN. Now let us see what is each and every one. Okay, so what is AND? AND is nothing but the keyword which specifies it is an AND gate. Okay, next G1. What is G1? It is a name assigned to this specific instantiation. Okay, it is your wish. It is your wish. Within brackets, we have to specify the outputs and inputs. So how many outputs will have? Only one output, that is O. How many inputs? It can have n number of inputs. That is why I1 to IN. Okay, this is how we have to instantiate the AND gate primitive. Okay, so starting, this is the, once again, this is the AND is the keyword for AND gate. G1 is the name assigned to this instantiation of AND gate. Okay, O is the output. I1 to IN are the n number of inputs. Okay, always we have to mention output first and next inputs. Okay, next. So this you just read out all these things. Okay, so the AND module has only one output is here. Next, the first port in the argument list is the output port S. This is output port. Next, an AND gate instantiation can take any number of inputs S. It consists of any number of inputs I1 to IN. Okay, next, the upper limit is compiler specific. Okay, that means the upper limits, how many number of inputs that we can access, that depends upon the compiler specific, Verilog compiler specific. Okay, next, a name need not be necessarily assigned to the AND gate instantiation. That means this one, this G1 is optional. What is G1 here? It is the name which we assigned to this AND gate instantiation. Okay, so this is optional. It is your wish whether you have to give this name or not. Okay, next, this is true of all the gate primitives available in the Verilog. Okay, that means there is no need to mention this name to this specific instantiation. It is your wish whether you want to specify or not, that is your wish. Okay, it is true not only for the AND gate primitive but also for all other gate primitives which are available inside the Verilog. Okay, so that means the name is optional. Okay, next, now let us see the example. So here there is one module. Okay, here there is one module to instantiate the AND gate primitive and test it. Okay, so what this module comprises? It is nothing but to instantiate the AND gate primitive. That means we are calling that AND gate primitive which is already available in the Verilog and test it, and we are writing some program to test that AND gate. Okay, now that is nothing but the stimulus program for testing the AND gate G1. Okay, so what is stimulus program? Stimulus means excitation, giving input combinations. Okay, that is why we are calling it as a stimulus program for testing the AND gate G1. What is this AND gate G1? This is nothing but this one, AND gate G1, AND gate primitive. Okay, that means here what we are doing is AND gate primitive is already available in the Verilog. Okay, now we are going to instantiate that AND gate primitive. Okay, okay, we have instantiated, we have called. Next, what is the next step? We have to write the test input combinations for this particular AND gate to check whether it gives the proper output for all the possible input combinations or not. That means we have to write the test bench. Yes, test bench. Okay, so the combination of these two is nothing but the stimulus program for testing the AND gate G1. Okay, here we'll instantiate the AND gate primitive and we write the test bench. Okay, now every Verilog program always starts with a keyword called module. This is module. Okay, and by the side, what is this one? This is nothing but name of the module. Okay, now what is the name of the module? In this case, it is given as some test underscore end. That means we are going to test the AND gate for giving all the possible input combinations. Okay, now this is module is the keyword and test underscore end is the name which is given to this module. Okay, and next reg a1 comma a2. What is this a1 and a2? Those are nothing but inputs. A1 a2 inputs, we are declaring them as a reg type. Okay, reg type. Next, what is the next statement? While b. What is b here? B is nothing but the output of the AND gate. So we are declaring it is as a wire data type. Okay, now here the inputs A1 and A2 are reg data type and B as the output which is the of wire data type. Okay, how we can know that A1 A2 are the inputs and B is the output? You just observe here. Here it is available. This is nothing but AND gate instantiation. Yes or no? This is nothing but AND gate instantiation. This is AND gate primitive name. This is the name G1 assigned to this AND gate primitive. Now this B is the output. A1, A2 are the inputs. Okay. Now here the same thing we have mentioned with the data types. Okay. Next, initial. So what this initial will convey you? Initial tells that is the initial assignment has been done only once throughout the whole routine of the program. Okay, initial means only once we are assigning the values initially throughout the whole routine. Okay, next begin. Okay, all the block of statements inside the module should always start with a keyword called begin and should end with a keyword called end. Okay, that is why it is called begin and some statements and end. Okay, now inside this we have written some statements. Now let us see what are these. Here in all these we have mentioned what is A1, what is A2, what is A1, A2, A1, A2, all these things. What is A1 and A2? These are nothing but the inputs for the two input AND gate. That means here we are giving different possible combinations for the inputs A1 and A2. Why? To check the functionality of the AND gate, whether it is giving proper output or not. Okay, now see here. So here first initial, what is the initial assignment given to A1 and A2? A1 is assigned to 0. Very good. A2 is also assigned to 0. Now what is the initial assignment to A1 and A2? 0, 0. Now you just observe on the right side. So A1 is 0 and A2 is also 0. Okay. Next, hash 3. What is this hash 3 represents? It represents after 3 time steps. After 3 time steps. Okay. That means you are going to change the values of A1 or A2 after 3 time steps. Okay. So hash 3 represents after 3 time steps. Okay. What you are doing? We are making A1 equal to 1. Okay, initially at 0, A1 is 0, A2 is 0. But after 3 time steps, we are making A1 equal to 1. Okay, now what happens to A2? A2 we are not mentioning anything here. That means A2 will remain same. That is A2 is 0. Now look into right side. So after 3 time steps, okay, after 3 time steps, what happens to A1? A1 is 1. A1 is 1 here. Okay, and what happens to A2? A2 is 0. We have not changed A2 here. A2 is 0, previous value. So A2 is 0. Okay, next. After 1 second, let us take after 1 time step. After 1 time step, what happens to A1? A1 is again changed to 0 from 1. Now what happens to A2? A2 is not mentioned here. That means again A2 will take the previous value. Okay. So after 1 time step. So up to here how many time steps we have completed? 4. So 3 plus 1. How many? 4. That means after 4 time steps, A1 is 0 and A2 is same as before 0. Now look into here, right side. So after 4 time steps, your A1 is 0 here. A1 is 0 here. Okay. And what is A2? A2 is 0 here. A2 is 0. Okay. Is it okay? Next, after 2 time steps. Now we are going to change the value of A2. Now A2 is 1. What about A1? A1 we are not mentioning anything. That means A1 will take the previous value, this one. Okay. Now after 2 time steps, up to here how many? 3 plus 1, 4, 4 plus 2, 6. That means after 6 time steps, A2 will be 1 and A1 will be 0. Now look here. After 6 time steps, A1 will be 0 and A2 will be 1. This one. Okay. Next, after 4 time steps, again you are changing the value of A1. But A2 is no change. Okay. Now 3 plus 1, 4, 4 plus 2, 6, 6 plus 4, 10. After 10, A1 is 1 and A2 is also 1. Here. After 10, A1 is 1, A2 is also 1. Okay. Next, after 3 time steps. So up to here we have count of 10 time steps plus 3, 13 time steps. After 13 time steps, what happens to A2? A2 is becoming 0. But what happens to A1? A1 is previous. That is 1. Okay. So at 13, A2 is 0 and A1 is 1. Okay. Next, last 1. So up to here we have a count of 13 time steps. So 13 plus 1, 14. After 14, again the A2 value is changed to 1. Okay. Now what happens to A1? So previous, this one. Okay, this one. So now after 14, your A1 becomes 1, A2 becomes 1. So like this, we have written the text bench. That means we have taken a 2 input AND gate. Inputs are A1 and A2, output is B1. Okay, now here we are defining the input values. What should be A1, what should be A2. Like the different combinations we have applied here. This is nothing but the stimulus program, giving inputs to your design. Giving inputs to your design. That is nothing but a stimulus program, stimuli. Okay, now these things. Okay, did you understand? Okay. Now you observe here, did you get all the combinations? So two input AND gate means how many combinations will get? Maximum four possible input combinations. What are they? 0, 0, 0, 1, 1, 0, 1, 1. Let us see whether all these combinations have obtained in our test bench or not. Okay. So here 0, 0. Okay, it is available. 0, 1, it is available. 1, 0, yes, it is there. And 1, 1, yes, it is there. So we have considered the two input AND gate. So for the two inputs, we'll get four input combinations. So all the four input combinations are available in our test bench. Even some of them are repeated. That is, don't bother about that. Nothing wrong. Okay. So all the four possible input combinations we have mentioned here. That is nothing but a test bench to test your AND gate, whether it is functioning correctly or not. Okay. Now we have written test bench. Okay, up to here it is well, but where we apply this test bench, to which circuit you will apply to this is this test bench, to which design, to which circuit, to which gate you are going to apply this test bench. Okay, which one? Nothing but AND gate. Here you have instantiated the AND gate. Okay, this is AND gate instantiation. That means whatever the test bench you have defined here, all the input combinations are going to apply to this AND gate instantiation. Okay, is it okay? Okay, next. Next you'll see. So what is this? Initial dollar monitor. This is nothing but system task. What we have discussed in the last classes. Okay, dollar monitor within brackets some arguments, dollar time comma a1, okay, equal to percent %b. What is percent %b? It is nothing but format specifier. That means we are going to represent a1 value in the form of binary. Percent %b means binary, a2 also in the form of binary, and b output also in the form of binary. Okay, now what are the outputs? Sorry, inputs a1, a2 and b. Just we have mentioned the format specifies for this. Okay, this is how we have represented the dollar monitor statement. So what is the function of dollar monitor? Dollar monitor always keep track of values of these variables which are present inside the bracket, and whenever any change happens on this a1 or a2, then that will be displayed on the screen. That will be displayed on the screen. So once again I am repeating, dollar monitor always keep track of the change of values of a1 or a2. Okay, a1 or a2 and b. Okay, on the screen, on the display on the screen. Now what is this dollar time? Dollar time is nothing but it will, dollar monitor will display the simulation time. Dollar time means a simulation time on the screen. Okay, that is what we have observed here. This is nothing but dollar time, simulation time at 0 time step, 3 time steps, 4 time steps, 6 time steps, 10, 13, 14. This is nothing but simulation time. Please observe here. This is nothing but simulation time. How it is displayed? By using this dollar time statement. Okay, dollar time. Is it okay? So what is dollar monitor? It always keeps a track of this, any change of values of these variables a1, a2, b. Then whenever any change happens on this, immediately it will be displayed on the screen with the simulation time, Okay, now let us see how it has been worked. So you see this example, you see this one. Okay, now this is the simulation time. I think you understood this one. Simulation time, that is happened with this dollar time. Okay, now we'll see how this dollar monitor works. Okay, now you see what is a1 0, a2 0. Okay, initially what is a1 0, a2 0? Initially we have mentioned, therefore initial values have been displayed on the screen. Okay, now in this case, in the second case, a1 is changing. A1 is changing from 0 to 1. A2 remains the same. Okay, that means A1 changes, A2 remains the same. That means some change has been happened. Then definitely it has to display, because that is the definition of dollar monitor. Dollar monitor will display any changes of the value of the variable on the screen. Okay, that is why it is displayed. Next, you see the next one. A1 is 0, A2 is 0. That means A1 is again changed from 1 to 0, but A2 remains same. That means some change happened. That is why it is displayed. Next, A1 is 0, A2 is 1. That means A1 is 0, same as previous one. But A2 has been changed from 0 to 1. That is why it is displayed. Okay, next, A1 is 1. That means from 0 to 1, change. A2 is 1, remains the same. Since A1 change happened, it is displayed. Next, A1 is 1. That means same, previous, no change. But A2 has been changed to 0, from 1 to 0. That means change happened. Next, last one. A1 is 1, A2 is 1. So A1 is remains the same, but A2 has been changed from 0 to 1. That means whenever any change happens in the values of either A1, A2 or B, then it will be displayed on the screen. That is the function of dollar monitor. That is the function of dollar monitor. Okay. Next one. Initial $100 finish. Sorry, initial $100 finish. What is this thing? Sorry. Hash 100 means nothing but after 100 time steps. Dollar finish means nothing but to stop the simulation. To stop the simulation. That means after 100 time steps, the simulation will be stopped. Okay, now how you end all this entire program? By using a keyword end module. So this is how we have to write the test bench to test the functionality of the circuit. Okay, so remember, there is a lot of difference between a test bench and the main program. Okay, for example, if you take the half adder. Okay, so what are the inputs for the half adder? Some two inputs, A and B. What are the outputs? Sum and carry. Okay, what is the expression for the sum? A XOR B. How you get the output? Some carry equal to A and B. This is how we describe the function of the half adder. Okay, so all this entire description of half adder we'll write in the program. So and so half adder design, so and so inputs, so and so outputs. Now output is obtained by using the expression AX or B, and some another output carry is obtained by writing the expression A and B like this. We'll describe the function of this circuit in the form of a code. Okay, that results the design description of your circuit. Design description of your circuit that we will write inside the module that becomes the main program of your design. Okay, now coming to other side, test bench. Now what is this test bench? You have designed the half adder. You have designed the half adder, but who will check your half adder? Who will check your half adder? We have to give some inputs to check whether the half adder is functioning correctly or not. Where we write these input combinations? That means we require another program to write all the possible input combinations to check the functionality of your half adder. Now what is that program? That is nothing but a test bench program. Okay, a test bench program is the program which also always starts with a keyword called module, where we write all the possible input combinations of your design, and this can be applied to your design and to check the functionality of the circuit. That is the test bench. So what we have discussed so far, we have taken an example for half adder. So whatever the design description you are giving for the half adder, that will write in some program, that is main program. And in order to test that half adder, we are writing another program that is called test bench program, where we write all the possible input combinations to check your half adder circuit. That is called test bench. Okay, that means you have to develop a program for designing your circuit, and another thing, you have to write a test bench program in order to test your circuit. So both are different. So please be careful. Okay, please be aware of it. Both are different. Your module description program is different. Your design description program is different. Your test bench program is different. Okay, so please remember that. Next, I think you have understood this thing. Okay, next. So this is nothing but the this explanation of this program. Okay. Can we read once this all these steps? Okay. So first one, the module test underscore hen has no port because it is the test bench. Okay. Here we are not mentioning any ports, input ports and output ports, because it is a test bench. Okay. Now here there is a gate instantiation and the gate instantiation. Here we'll mention, but here there is no need. Okay. It instantiates the end module once. Yes, we have instantiated the end module here. We have instantiated the end module. Okay. Next, the test input sequence is specified within the initial block. The sequence of statements between the begin and end statements together form this block S. So test inputs we have written here between begin and end, that is inside the initial. Okay. Next, the keyword initial signifies the settings done initially, that is only once for the whole routine that we have discussed in the previous example. Okay. Next, the first set of statements within the initial block a1 equal to 0, a2 equal to 0 make a1 equal to a2 equal to 0 at 0 simulation time. That what we have observed here, 0 simulation time. Here 0 simulation time, a1 is 0, a2 is 0. Okay. Next, after 3 time steps, a1 is set to 1 but a2 remains at 0. Yes, after 3 time steps, a1 is set to 1, a2 is set to 0. Sorry, a2 remains at 0. Okay. So the expression $3 means what? Sorry, hash 3 means after 3 time steps. Okay. Next, the program displays the variable values. Okay, that is the values of O output A1 and A2 whenever any one of these changes. Okay, that is nothing but your dollar monitor. Okay. Next, a pair of variables A1 and A2 are declared in the program S, and the values stored in them are given as inputs to the AND gate instantiation S, because A1, A2 are the inputs. Whatever the values you give to the A1 and A2, those can be applied to your AND gate instantiation. Next, a variable not declared in the module is by default taken as a net of wire type. It is also taken as a scalar. The same is true for all modules in the Verilog S. Okay. If any variable is not declared in the module, then by default it is taken as a net of wire type. Okay. It will default, it will take it as a wire type. Next, the term $time in the $monitor statement signifies the running time of the program. Running time of the program. Okay, that is called simulation time. Running time of the program. Okay, next here this one. This one 0, 3, 4, 6, 10. This one. Okay, running time of the program. Next, here it causes the value of time at the instant of capturing the data for display to be displayed. Okay. Next, the statement hash $100 finished signifies that the program will stop simulation and exit the operating system at the end of 100 time steps. This is what we have explained now. What I have explained now. Okay. So, but you please read out all these points, then you can easily understand this program. Okay, what is what? Okay, what is initial, what is begin, what is these statements, what is end, what is this end gate instantiation, what is dollar monitor do, what dollar time will do, what dollar finish will do. Everything is given in this text. You please go through this text. Okay. Next, so this is how the output is displayed. So after running this program, So how we are getting the output? This thing. This is nothing but the simulated output. This one. So this is the simulation time, running time of the program 0, 3, 4, 6, 10, 13, maximum 14. Okay. So how you got this? By adding all these things. This. Okay. 0 to 14. Next, what is value of A1? What is value of A2? What will be the output? Okay, so 0 0 means AND gate output is 0, 1 0 means AND gate output 0, 0 0 output is 0, 0 1 output is 0, 1 1 output is 1, 1 0 output is 0, 1 1 again 1. That means we have verified the functionality of the AND gate by checking all the possible input combinations of your AND gate, that is 0 0 0 1 1 0 1 1. Yes, that means your AND gate is functioning correctly. Okay. Okay. Next truth table for the AND gate primitive. Okay, now let us see what is the truth table for this AND gate primitive. Okay, generally in the previous semesters I think you have studied the digital circuit subject. In that, if you take the truth tables for the logic gates, there will observe only two logic values, either 0 or 1, 0 and 1. Okay, but here in the Verilog hardware description language we define the logic values as 4 types. Okay, so in the last classes we have discussed those things. Logic values are of 4 types, that is 0, 1, X and Z. Okay, 0, 1, X and Z. Okay, so if you take the 2 input AND gate, now you take these combinations. The input 1 may be 0, 1, X, Z. Okay, the second input may be again 0, 1, X, Z. Now we'll get the truth table like this. Okay, let us see one case. So this is Z. This is 0. So Z 0. What will be the output? 0. Next, Z 1. What will be the output? X. Z X. What will be the output? X. Z Z. What will be the output? X. Okay. That means if any one of the input is 0, the AND gate the output will be 0. In the remaining cases, it depends. Okay. So like this, we have to verify this truth table. Okay. Let us take another case. If you take this one, 1. Okay, 1 0. Okay, 1 0 output is 0, 1 1 output is 1, 1 X output is X, 1 Z output is X. Okay, this the truth table we have to remember. Okay, now so this is nothing but explanation of this truth table. Okay, if any one of the inputs to the AND gate instantiation is in the 0 state, its output is always in the 0 state, that we know. Okay, it is irrespective of whether the other inputs are at 0, 1, X or Z state. Yes. Next, the output is at one state if and only if every one of the input is at one state. Yes, if both inputs are 1, then only the output is 1 for the 2 input AND gate. Okay. Next, for all other cases, the output is at the X state. This means only if any one of the input is 0, the output is 0. If both inputs are 1, the output is 1. And remaining all cases, the output is in the X state. X state. Here, you observe here. X, 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 all these things are X. Okay. So once again, in a 2 input AND gate, if any one of the input is 0, the output is 0. If if both inputs are 1, then output is 1. Okay. Other than these two cases, in all cases the output is X. Okay, note one thing, you make a note that the output is never at the Z state, that means high impedance state. That means the output will never be at a high impedance state. Okay, because in the truth table we never get the outputs as a Z state. You please observe here, there is no Z at all. That means the output is never enters into the high impedance state. Okay, not only this for AND gate, it is also true for all other gate primitives which are available in the Verilog. Okay, next. Okay, so with this we have completed the AND gate primitive. Okay, once again, once let us go to the syllabus. This one, AND gate primitive. That means AND gate primitive means, first of all, you have to define What is a primitive? Because it is readily available inside the Verilog, as all basic gates are available as primitives in the Verilog. Now, how to instantiate this AND gate primitive? Yes, we have instantiated. Next, how to test this AND gate? Okay, we have seen some with some example. We have written the test bench. We have instated the AND gate. We have observed the output. Yes, okay, with some statements also, with some system tasks also. Okay, and finally we have observed the truth table for the 2 input AND gate primitive. Okay, next what is the next topic? Module structure. Module structure. Okay, so already we have discussed this module concept in the previous classes. Yes or no? Now let us just once review those concepts. Okay, so the first statement of a module starts with a keyword module. Yes, we have already known about this. Next, it may be followed by the name of the module and the port list if any. Yes. Yes or no? Okay. First, always your Verilog program starts with module. Okay. By that side, we'll always mention the name of the module, and within brackets we have to mention the ports, output ports, input ports, if in-out ports also. Okay, if they exist. This is what we have mentioned here. Just look into this. This is, for example, if you take this end G1, B, A1, A2, end is the module, G1 is the name of the module, this is output, this is the inputs, these are the inputs. Okay, next. All the variables in the ports list are to be identified as inputs, outputs, or inouts. Okay, whatever the variables you are mentioning inside the brackets, we have to identify them as input port, output port, in-out ports. Okay, like this. Okay, A1 and A2, that should be considered as a input, B1, B2 output, C1, C2 in-out. Okay, like this we have to identify. We have to identify the port list. Okay, the, okay. Next, the ports and other variables used within the body of the module are to be identified as nets or regs with specific types in each case. Yes, what we have done here. So here we have used B is the output port, A1, A2 are the input ports. So A1, A2 we are declaring it as a reg type, reg type, where B we are declaring it as a wire type. That what this point says. This one. The ports and other variables used within the body of the module are to be identified as nets, net or wire, okay, or registers with specific types in each case. Next, the last statement in any module function is the keyword end module. Yes or no? This one, end module, last statement. Okay. Next, the comments can appear anywhere in the module definition. Okay, wherever necessary, you can write the comments. Either it may be a single line comment or multi-line comment. Okay, this is nothing but module structure. This already we have discussed in the first unit. Okay, again, as it is also given in the second unit, again we are reviewing those concepts. Okay, so module structure. Any Verilog program starts with a keyword called module. Okay, by that said, name of the module. Within brackets, we have to mention the outputs and inputs. Okay, now whatever the outputs and inputs we are giving inside the brackets, those must be defined, whether it is an input port, whether it is output port, whether it is an in-out port. That is done. Okay, and next we have to write some statements. Okay, okay, now we have to declare the variable types, whether it is a net type or wire type or reg type, register types. We have done that also. Okay, now if you need any comments, you can write inside the module. Either we can write single line or multi-line comments. Okay, and next we have to end this module by using a keyword end module. Okay, this is how we have to define the module structure. Module structure. So please remember, once again I am repeating. So module means it may be a main program of your design or it may be a test bench. Okay, so test bench module is there or your main design description module may be there. Okay, so both are modules only. We call them as a modules only. Even it is design description of your logic circuit, or even it is a test bench for testing your circuit, whatever it may be. Okay, we write them in modules. We call it as a main program module or design description module in one case. In another case, we call it as a test bench module. Test bench module. Okay. Okay. So in today's class, we have discussed about this gate primitives and gate primitives and module structure. Okay. So in the next class, we'll discuss about this other gate primitives. Other gate primitives means except AND gate, that is NAND, NOR, XOR, XNOR, buffer, NOT, all these things. Okay. Thank you. Have a nice day.